Welcome to this episode of Mentors at Your Benchside, the podcast giving you advice, tips and tools for getting the most out of your research. I'm Thomas Warwick, and today I'll be talking to you about water of crystallization. When I was a lab technician, I was often asked to find chemicals like magnesium chloride .6H2O or aluminium chloride .3H2O, etc. Do those numbers at the end of the formula matter, and can you still use them? In many cases, the answer is no, it doesn't matter, and yes, you can still use them. Maybe you've asked yourself this question recently, or perhaps someone has told you so, but didn't explain why. Those water molecules are water of crystallization, and they seldom matter to your experiments, except sometimes they do, and they're a prime example of a broader phenomenon, solvent of crystallization, which will undoubtedly matter at some point. What is water of crystallization? When a chemical crystallizes from a solution, say during industrial preparation, it may co-crystallize with some solvent molecules. These solvent molecules become an integral part of the crystal structure of the chemical in question. When the solvent is water, any extra molecules that co-crystallize with the chemical will be water. This is called water of crystallization. As mentioned, this water, when present, is an integral part of the crystal structure of the chemical. The precise structure and arrangement of the water in the crystal structure doesn't matter because we're not solid-state scientists. The properties that do matter are, it exists, it occupies definite positions, and it often helps hold the crystal together through hydrogen bonds. Water of crystallization, whenever it's present, is there because it's energetically and structurally favourable to include it when the crystal is forming. As I've said already, it's integral, as much a part of the crystal as any other part. Check out the corresponding article for a handy figure that explains what I mean. It may also incidentally impart desirable properties to a crystal, such as increased solubility, hardness, or conductivity. For example, ruthenium chloride is insoluble in water, but ruthenium chloride trihydrate is soluble. Anhydrous aluminium chloride is a catalyst and strong Lewis acid, but hydrated forms are much weaker acids and unsuitable as catalysts in organic chemistry. Perhaps most crucially is when the solvent of crystallization isn't water, but another more intrusive solvent that this information will benefit you. We'll get to this later. Here are 3 examples of water of crystallization. Number 1. Gypsum. Water of crystallization is responsible for the setting of gypsum plaster, also called calcium sulfate or CaSO4. We mix the dry gypsum with water, which sets as calcium sulfate dihydrate, or CaSO4.2H2O. Without the 2 molar equivalents of water, we wouldn't get a wall or sculpture. Instead, we get something like the bag of fine powder that we started with. That's to say, the water doesn't all evaporate. Some of it sticks around during the crystallization process and is, in part, necessary for the structural properties of plaster. Number 2. Protein. Another fantastic example of water crystallization are protein crystal structures. All living organisms on Earth are water-based. When their constituent proteins are crystallized to solve their structure, they drag some water molecules with them. If they didn't, they'd denature, because the water of crystallization is part of their quaternary structure. Note that phrasing it like this is the tail wagging the dog. It's more accurate to say that if the protein molecules in solution were totally dehydrated, they would denature, and denatured proteins do not crystallize because they're structurally heterogeneous. Number 3. Metal hydrates. These represent chemicals that will probably make you ask the question at the top of the article. Included are species such as iron 3 chloride dihydrate, 2 waters, magnesium 2 chloride hexahydrate, 6 waters, nickel 2 chloride hexahydrate, also 6 waters, and anhydrous aluminium 3 chloride, no waters. We use them extensively in biology. For example, iron chloride is an additive in some cell growth media. Magnesium chloride is a PCR additive. Nickel salts charge metal affinity columns, and anhydrous aluminium chloride is a catalyst in Friedel-Crafts acylation. Plus, we mix them in various ways to impart desirable properties to our buffers and solutions. And on a bit of a random point, anhydrous metal salts are usually quite hygroscopic. They tend to attract moisture from the atmosphere. So take care to seal them properly after use, otherwise you won't be able to accurately determine the concentration of any such reagent in your experiments because of the extra mass added by the water. Can I still use it? Does water of crystallization matter? So, you've plucked a reagent off the shelf and noticed it has a different number of water molecules at the end of its formula than the ones specified in your protocol. Does it matter, and can you still use it? In short, no, it doesn't matter, and yes, you can use it, unless You don't intend to dissolve the reagent in water, the final percentage of water in your solution or experiment really matters, or you have to work under anhydrous conditions. Why so? Because the water of crystallization is labile, it won't stick around upon dissolution. If you dissolve the reagent into water, the water of crystallization will simply add to the bulk volume of the water, so it won't do any harm. Note that I'm assuming that you usually intend to simply dissolve the reagent and crack on with an assay, rather than say doing fancy pressure and conductivity measurements on the crystals themselves. Bite Size Bio is a biology blog after all. Just remember to weigh out the appropriate mass of the reagent so that your concentrations are accurate. Every water molecule contributes 18 grams per mole of relative mass. That means that the water of crystallization sometimes contributes more by mass to the crystal than the species we're interested in and call the reagent by. Here's an example calculation. Let's say a protocol asks you to prepare 500 ml of 0.5 molar anhydrous magnesium chloride by dissolving 23.8 grams into 500 ml. But you only have the hexahydrate form in your lab. How much should you weigh out? The molecular weight of magnesium chloride is 95.2 grams per mole. The molecular weight of water is 18 grams per mole. Thus, the formula weight of magnesium chloride.6H2O is 95.2 plus 6 times 18, which equals 203 grams per mole. So, dissolving 203 grams in a litre gives a 1 litre solution of a 1 molar solution. Dissolving 101.5 grams in 500 millilitres gives 500 ml of a 1 molar solution, half the volume. Dissolving 50.8 grams in 500 millilitres gives 500 ml of a 0.5 molar solution, half the molarity. So you will need to dissolve 50.8 grams in 500 ml. Other molecules of crystallization. Molecules other than water can end up as solvent of crystallization. It depends on the solution from which a reagent is crystallized when it's prepared. Any species that the reagent was initially solubilized in or with could get encapsulated in a crystal if it's sterically and energetically favorable for it to incorporate. For example, acids like hydrochloric and sulfuric acid, alcohols, ethers, and acetone can co-crystallize with the primary reagent, as can additives such as sulfate, carbonate, and glycols. So beware. Figure 2 in the corresponding article shows a good example of acetone of crystallization. The good news is the solvent gets included on the reagent formula, usually found on its container. It's specified after an interpunct, also called a middle dot. For example, reagent.toSolvent. Ultimately, you have to decide, case by case, if any solvent of crystallization is going to impact your experiments, or at least be aware of it to caveat your results and troubleshoot your experimental design if things go awry. So when might solvent of crystallization matter? Here are 2 real-life examples. Medicinal chemists doing fancy organic synthesis to prepare lead compounds may need to work under anhydrous conditions. The classic example is the Grignard reaction to make new carbon-carbon bonds. Here, the halogenated reagents must be kept dry or they break down. Medicinal chemists do all sorts of fancy stuff though, and for the rest of us, here are 2 examples of solvent of crystallization in biology labs. Number 1. Tris-HCl. Tris-HCl or Trisma is a version of Tris base that's often spoke of as pre-buffered Tris, because it has a lower pH than Tris base when you dissolve it. True, it does, but more precisely, it's Tris base crystallized from hydrochloric acid. Some of the hydrochloric acid molecules come along for the ride. Crystals of it actually contain a 1-to-1 stoichiometric ratio of Tris base and hydrochloric acid. This matters for a few reasons. First, Tris base and Tris-HCl have different relative masses, so weighing out the same amount regardless of which form you're using will result in a different final concentration. Tris base has a relative mass of 121.1 grams per mole. Hydrochloric acid has a relative mass of 36.5 grams per mole. Therefore, Tris-HCl has a relative mass of 157.6 grams per mole. Bear this in mind the next time you're absent-mindedly following a recipe to prepare 10 times STS page running buffer. Second, depending on the final desired pH of your solutions, you could accidentally add more salt to your experiments than intended. If you dissolve Tris-HCl and the pH is lower than you required, and then you add some NaOH to increase the pH of your solution, you're adding extra salt. The sodium cations come from the NaOH, and the chloride anions come from the HCl. In such cases, it's better to use regular Tris and not overshoot your intended pH value. Number 2. TSEP-HCl. TSEP is a reducing agent that, unlike its alternatives, BME and DTT, does not readily hydrolyze in aqueous solutions. Its stability makes it great for experiments that last several hours or days. However, we purchase it as TSEP HCl. So, for every molecule of TSEP in the crystal, there's a molecule of hydrochloric acid. The hydrochloric acid of crystallization means that the pH of TSEP HCl solutions is low. Additionally, adding it directly to experiments could lower the pH and influence your results. That's why we should buffer TSEP HCl solutions to a relevant pH using sodium phosphate or whatever buffer isn't going to impact your experiments. If you really desperately need to remove solvent of crystallization, here's one thing you can try. Heat your reagent up in a lab furnace as hot as you dare. Eventually, the solvent of crystallization should vaporize. Just check that the reagent doesn't do something dreadful at elevated temperatures like exploding or producing toxic vapor. Note also this could harm your reagent unless it's some sort of rock-hard mineral. It could also melt it or ruin its crystallinity. So think about if this matters. And you probably won't know whether the process has worked unless your reagent is a common one that's tabulated in the literature, or you can replicate the conditions in a thermogravimetric analyzer. So that's everything you need to know about water of crystallization. Check out the episode description for links to related articles and resources, and don't forget to subscribe to the podcast to get more help and advice from mentors at your bench side.